Swati.
Good evening, ma'am.
Good evening, Swati.
Yeah,
Some
ma'am.
like this read.ai. Can you please?
Yeah, I'll just remove them.
Don't think that is necessary.
Yeah, I'll just remove that.
Okay, please remove that. Thank you.
Yeah.
Don't give permission for people to add such things. Okay.
Yeah. No, ma'am. It's like automatically it's get.
Automatic. It's
Yeah.
Lavanya added is mentioning.
No. This is just a read.ai. It's automatically gets
Okay.
added to this
Yeah,
thing.
please do that. Thank you. Can we start or we'll wait for some?
I was just thinking to let's wait for 2-3 minutes
Sure.
because only 10 people have joined, so we can just
Right.
wait for two,
Yeah,
three
yeah.
minutes.
You tell me when I can start and I will do that.
Okay, ma'am. Sure.
Thank you.
Okay, ma'am. We can start with the
Okay.
session. Okay. So good evening, everyone. So today we are having a revision session for week 9 to 12. Okay. So just wanted to clear that the doubts will be taken only the conceptual doubts will be taken from week 9 to 12. No general doubts will be clarified or any specific questions or assignment based questions won't be taken. Okay, all the general doubts or the questions that you're having regarding any questions or activity questions, practice assignment, that will be taken on the next session. Is that clear, everyone? Is that clear?
Yes, ma'am.
Yes or no? Okay, fine. Okay, ma'am. We can start with the session.
Thank you. Thank you, Swati. Good evening, everyone. As Swati mentioned, the purpose of this 2 hour session is to just revise the conceptual understanding or to just give you a conceptual revision of the week 9 to 12, which is about random variables, discrete distributions, and continuous distributions. And again, as she mentioned, we are not going to look at any particular or a specific problem that is a part of an activity or assignment. Rather, we are just going to revise at a conceptual level. Please feel free to send your conceptual doubts and everything either on chat or after every uh, topic. I'll just pause for a minute and take questions. Okay. So let's get started. So the agenda for today is, as you can see on the screen. I hope the screen is visible. Yeah.
Yes, ma'am. It's
Yeah.
good.
Yes, as you can see on the screen, we start with a basic review of the concept of a random variable. probability mass function, probability density function, the cumulative distribution function, and notion of expectation and variance. And then we review a few discrete distributions. And you can see that we are going to start with the binomial experiment. And of course, we will talk a bit about even Bernoulli at that point of time. But the primary idea is to introduce binomial, hypergeometric, and Poisson distributions. And we are going to look at a few continuous distributions. Now let's get started. What is a random variable? If you recall from the probability, when we introduced probability as a concept, we started by the notion of a random experiment. So a random experiment is nothing but an experiment whose outcomes are uncertain. And then we said that the set of all outcomes of a random experiment is what we refer to as the sample space. Now, typically what would happen is when this random experiment is performed, we might not be interested in the details of the experimental result. That is, when I am tossing a coin twice, I might not be interested in knowing whether I had two heads and a tail, or a head tail, or a tail head. But I might be interested in some value, that is how many heads were there in an outcome. And that is what I meant. I think we want to convey is I might not be interested in the actual experimental outcome. It could be a head tail, or it could be a tail head, but both these outcomes are giving me two heads. So you are actually interested in the value of a numerical quantity. Looking at another example, which is often taken, which is I'm rolling a dice twice. I'm not interested on whether I had both of them were 1 or both of them were 2, or the first throw resulted in a 1, second throw resulted in a 2, but rather I'm interested in what is the sum of the outcomes. So then afterwards what happens is I'm not interested in the outcome itself, but I'm interested in something what I call is a function of that outcome. Now this function of a outcome is formally defined as I have a real valued function on the sample space, and these real valued functions is what we refer to as random variables. I repeat, random variables are formally defined as real valued functions on the sample space. That is, with each outcome of the sample space, I assign a real value number. So to just drive this further, let's look at the same example of rolling a dice twice. I know that the sample space has 36 outcomes, and you can see the 36 outcomes on your screen. Now, so instead of knowing each outcome, I want to now I'm interested in the sum of the outcomes. And I'm asking two questions. That is, the first question is, out of the outcomes, how many outcomes will result in a sum of 7? And out of the outcomes, how many outcomes will have the smaller of the outcomes, 3? So if both the outcomes are the same, I'm just going to take it as the smaller is the same number. So if you look at the way we can go about it to answer both these questions, I'm working on the same experiment and the same sample space. Now to answer the first question, how many outcomes result in a sum of the outcomes as 7? I can do it in two ways. One is I just look at the sample space. I know these are the sample space, and I can see that all these outcomes which I am depicting now are the outcomes that are giving me the sum of outcomes is 7. Now suppose I change it to sum of outcomes is 8. I know it is going to be this. Okay. So in a sense, the quantity of interest for me now is not the outcomes, but it is the sum of the outcomes. So what am I doing? I'm going to map every outcome here to a quantity which is nothing but the sum of the outcomes. Let me call that X. The minute I map, what is the value X will take for this outcome? It is going to take the value 2. For this outcome, it will be 3. For this is also 3. So you can see that for this it is 1, 2, this is 3. These outcomes it's going to be 4. And for this outcome it is 12. So X takes the value 2, 3, 4 up to 12. Is this clear? Is this clear?
Yes, ma'am.
Yeah. Okay. So now the next thing is, the next question is how many of the outcomes will have the smaller of the outcomes as 3? Similarly, for this outcome, the smaller of the outcomes, if the outcomes are the same, I'm going to take it as 1. So if I define that as y takes the value 1. Here the smaller is 1. For all these outcomes, the smaller of the outcomes is going to be 1. So let me rewrite whatever I have here. So you can see that all these outcomes, the smaller of the outcomes is going to be 1. For all these outcomes, the smaller of the outcomes is going to be 2. Here the smaller is 3. Here the smaller is 4. Here the smaller is 5. And here the smaller is 6. So the value this particular random variable takes is the value 1, 2, 3, 4, 5 and 6. So you can see that I have denoted X as the sum of outcomes, Y is the lesser of the two outcomes, and mapped every outcome to X and Y. And you can see that the experiment and the sample space are the same. Is this clear till here? What is the sample, the random experiment, the sample space, and mapping every outcome to the random variables defined as X and Y. Is this clear, please?
Yes,
Yes, ma'am.
Okay. So you can see that every outcome has been clear. Now let me just change the question. Instead of rolling the dice twice, if I had rolled the dice, I'm rolling the dice twice, but I have only a 4-faced die. That is, I have only 1, 2, 3, 4 instead of 1, 2, 3, 4, 5, 6. Okay. Now what is the sample space of this experiment? How many elements will be there in the sample space of this experiment?
No, 4.
Sample space will be
I just
16.
have 1, 2, 3, 4. So you can see that I won't have this, right? This will be my sample space now. Would you all agree?
Yes, ma'am.
Yeah. Okay. Now what is the value X would take in this case? What are the values X would take?
2, 3, 4.
2, 3,
4. Ma'am,
4,
2, 3, 4,
5,
5,
5,
8,
6, 7 and
7, and
8.
8.
8. Very good. What are the values Y would take?
1 to 8. 1, 2,
1,
4.
2, 3, 4.
1, 2, 3 and 4. So is this clear? So I now you can see that now are these the only two random variables I can define, or can I define anything else on the sample space? I can define Z, right? Maximum of the two outcomes. Just as I define the smaller of the two outcomes, I can define the larger of the two outcomes. Would you all agree?
Yes, ma'am.
Yes.
I can define the
Yes.
difference of the two outcomes also. Can I?
Yes.
Yes, ma'am.
Yes.
Right? Just as I defined the addition, I can define it. So you can see that even though the experiment and the sample space is the same, it depends on how I am mapping every outcome through the function, and this function is what I call a random variable. So the first step is to map every outcome to this random variable. The next is we are not just satisfied by looking at the random variable. We want to know more about this random variable. For example, I would like to know what is the chance with which the random variable or a sum of 7 would occur. That is my question. So the chance with which sum of 7 would occur would happen for this, it 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 would happen for this. In other words, I'm interested in knowing what is probability x equal to 7. I've just taken 7 as a number, but I'm interested in knowing what is probability x equal to 2, probability x equal to 3, and that is what I am interested in knowing. So the minute I'm asking the question, what is the probability that x takes a particular value, I need to map what is the relevant event. Okay, so if I'm looking at probability x equal to 2, what is the relevant event? X equal to 2?
1, 1.
Just 1, 1. It's a singleton. What is the probability x equal to 3? It happens with this and this. right? So you can see that for every probability of X taking a particular value, what I can do is I can map what is the probability of the relevant event, and I get what is we refer to as a distribution of this random variable. So what do I first have? I know that this is the sample space. From this sample space, I define what are X and Y. Now, once I define X and Y, I know what is the relevant event for each of the values. So now I can define what is the probability of the probability of X taking a particular value by mapping that to the probability of the event, because from probability class, I already know how to compute the probability of an event. So now I am coming up with what I refer to as a distribution of my random variable. Just as I did for X, I can do it for Y. So Y, what are the values X, Y can take? Again, let's go back here. What are the values Y can take?
Ma'am, 1, 2, 3, 4, 5.
1, 2, 3, 4. So what is the relevant event with 1? You can see that the relevant event with 1 is all these values 4, 1, 3, 1, 5, 1 and 6, 1. So similarly, I can do the same exercise for Y. I can find out what are the relevant events and what would be probability Y equal to 1. It would be the probability of this event happening, and I just map all of that. So I have now two random variables which I have defined on the same sample space following the same random experiment, and I have given, in addition to the definition, I have given what is the probability distribution. Is this clear?
Yes, ma'am.
Yes,
Right.
ma'am.
So now we are in a position to formally define what is a discrete random variable and what is a continuous random variable. Now, so first thing we need to remember is a random variable is nothing but a function from the sample space to the real value or to the real line. So that's why we are interested in what we call a real valued random variable. Now, if this random variable can take at most a countable number of possible values, I repeat, if this random variable can take at most a countable number of possible values, I call it a discrete random variable. It can take finite, it can also take countably infinite. So let's start with another sample space. I am tossing a coin till I get a head. So what is the sample space of this experiment? I toss a coin till I get a head. What is the sample space?
Head and tail.
Head, tail, head, tail, head.
Tail head.
Okay. Now my random variable is the toss at which I get a head. So what are the values this random variable will take?
1, 2, 3, 4, like that.
1, 2, 3, 4.
Oh,
So you can see that is it taking finite or taking countably infinite number of different values?
Countably.
countably
It is taking
infinite.
countably infinite. So is this clear? Whereas in the earlier case, my X was countably finite or countably infinite? When I rolled two dice, both my X and Y.
Yeah, finite.
Countably
Finite.
finite.
Countably finite. So is this clear? On the other hand, suppose the outcomes are numerical but they cannot be counted. For example, I am asking you to note down my random experiment is the time taken to reach the office from your home. So what is the sample space in this experiment?
Be infinite, madam. Time will
How would
not
I
be
tell
finite,
what is the
right?
sample space here? It is not, I can't express it as a discrete values as I did it in the earlier case, right? It is any
Yes.
time between 0 and infinity, right? Or some t where t lies between 0 and infinity. That is how I can write it, right? Now you can see that if the time is less than or equal to, so you can see here, the random variable here is not countable. It is infinitely divisible. Okay, so this is where I refer to as a continuous random variable. And as in the case of variable where we introduced the discrete and the continuous and said that if it is discrete, it typically involves counting. If it is continuous, it typically involves measuring. Okay, so a random variable, a discrete, has discrete points along the real number line, whereas continuous, it forms an interval. Is this distinction clear?
Yes, ma'am.
Yes, ma'am.
Right,
Yes.
very good. So you can see that when I look at different examples, suppose I'm looking at the number of students, I count here, right? Number of defective phones in a batch, again I'm counting. Number of goals, number of runs, I am counting. Number of missed calls. Whereas if I'm measuring body temperature, I measure or count body temperature? I measure. I measure the time taken to finish. I measure rainfall. I measure the speed. I measure the daily revenue is also not counted. You might count the physical money, but I report the revenue as a continuous measure. So is this clear? There are umpteen examples, but I've just given you a few to illustrate the concept of discrete versus continuous. Is it clear? Right.
Yes, ma'am.
Associated with any discrete random variable, I have the concept of what we refer to as a probability mass function. And the probability mass function is nothing but the probability with which that random variable takes a particular value. I repeat, the probability mass function, suppose x takes x1, x2, xn, these are general values. The probability with which x takes xi is what I call a probability of x equal to xi. And the distribution of this is what represented in the tabular form is called a probability mass function. Now, if I have countably infinite, it will be just x1, x2, x and so far. If it is finite, it is up to xn. Now, for example, if I come back to this, here you can see that I can write in this case that what are the values x took in the first case. When I looked at the sum, x was taking the values 2, 3, 4 up to 12, and I can get what is the probability of this x, right? Distribution of this x, and this is referred to as a probability mass function. Now, what are the two key properties of a probability mass function? One, because it's a probability of every xi has to be non-negative, and summation over all probabilities have to be equal to 1, because I'm mapping every unit of my sample space to a value, and I know probability of my sample space is 1. This probability of xi over all values should be equal to 1. So one of the common problems that you will be facing is to verify if something is a probability mass function. For example, if I have something where x is taking value 0, 1, 2, with probability 1 by 3, 1 by 3, 1 by 3. Is this a probability mass function?
Yes.
So
Yes, ma'am.
minus
Yes,
x
ma'am.
minus 1, 0, 1 with 1 by 3, 1 by 3, 1 by 3.
No.
Why not?
Yes, ma'am.
Should be positive or 0.
No, I'm just giving, this is x takes
Okay,
value
okay,
minus
sorry,
1, 0, 1 with probability.
It is yes, madam, yes.
Is it a probability mass function?
Yes.
Yes, ma'am.
It can
Yes,
take,
ma'am.
x can take, it is a real value, right? But if it is this following, minus 1 by 3, 2 by 3 and 1 by 3.
Then it is not.
It
Won't
is
be.
not, because this is violating the first rule, even though this is satisfied. Is it clear? So the first thing, you'll have a lot of problems where you'll have to verify if something is a probability mass function. The next important concept is what we refer to as a cumulative distribution function. This probability mass function is also a probability distribution function, because what it is telling us is basically the distribution of the random variable. Now, what is cumulative distribution function? Before going to cumulative distribution function, how do I geographically represent a probability mass function? The tabular form, I can represent it this way. So I know that this X takes discrete values. For example, I'm looking at being the IPL season. I think it would be a very good thing to look at what is the distribution of the runs scored in any cricket over. And you can see that these are the graphs that if any one of you has been following IPL, you see that these are the types that commentators very frequently show is, suppose in a number of runs scored in a cricket over, here we are only allowing up to 6 runs, but the way IPL 2026 is going, you can see that sometimes you can go up to 20 runs also, and the probability with which the runs have shown. So what you can see is the distribution, and based on this distribution, you can see that most of the runs scored in a, what is the highest thing? It is most of the overs have 1 run that is being scored. Is that clear? How would you interpret this particular probability distribution function? Which run has the highest frequency or the probability of being scored here?
M1.
1 run in a over. Is that clear?
Yes.
Yeah.
Yes.
Okay. So this is called a graph of a probability mass function. Now, using this graph, basically, why do we need a graph? The graph of a probability mass function will help us understand whether I have a skewed distribution or a symmetric distribution is something that would help. For example, what you can see on your screens now is a positive skewed distribution where the probability of x equal to 1 is high, and you can see that the probabilities of other values are coming down. Then similar mirror image of that is a negative skewed distribution. And this is also, if I have something where I have the probability, so if I have something of this kind, this is a symmetric distribution. So the probability mass function helps us identify not only what is the tabular or the distribution, but it also tells us something about the shape of the distribution. The next important concept that we are going to introduce is what is called a cumulative distribution function. So what we have seen so far is x is a random variable which takes values x1, x2, and now going to just focus on a finitely many number with probability of x1, probability of x2, probability of xn, which is nothing but, I know p of xi is nothing but probability x takes the value xi. This is a probability distribution function. But many a time we might be interested in knowing, for example, again, let me go back to the tossing of the 2 coins, the 2 dice, and I know x takes the value 2, 3, 4 up to 12. I might be interested in not only knowing what is probability x equal to 2, I might be interested in knowing that if I roll 2 dice, what is the chance that I'll get a total that is less than or equal to 3? Is the question clear? I might just not be interested in knowing what is the chance of me getting a total x equal to 2, but I might be interested in knowing what is the chance that I might be getting a total x is less than or equal to 3. So I quickly realize that this is same as probability x equal to 2 plus probability x equal to 3. That is, I am accumulating or cumulating the probability distribution of x equal to 2 and x equal to 3. And this is what we refer to as a cumulative distribution function. Is it conceptually clear?
Yes, ma'am.
Right? So how do I formally define the cumulative distribution function? The formal distribution is, suppose I have x1 is less than x2 is less than x3, then f of a, this is again, once I tell it's a distribution function, this distribution function is defined on the real line to 0, 1, because this is a probability. Probability lies between 0 and 1. So this function is defined as probability x is less than or equal to a. It cumulates, or it is a cumulative distribution function. Okay, and it is abbreviated as CDF, whereas the probability mass function is PMF. The cumulative distribution function is CDF. So let's go back to this question. If I am interested, what is the chance that that less than 2 runs are scored in a cricket over? less than 2 runs, less than or equal to 2 runs are scored in a cricket over. What would you do?
0.75.
Less than or equal to 2 runs, you're going to add these three probabilities together. Would you agree?
Yes,
Yes,
0, 1,
ma'am.
and 2.
Right? Yeah. Less than or equal to 4, I'm going to add all of them. Right? Now I can add what is, if I ask you what is the chance that greater than 2 runs are scored in a over. What would I do?
Add up 2 to 6.
Ma'am, probability of 3 plus
This
probability
plus
of
this plus this, right? So the first one I asked probability x is less than or equal to 2. The next I asked what is probability x is greater than 2. And you know that this probability x is greater than 2 is 0.25, right? Okay, what is this probability? 0.75. So this is same as 1 minus probability x is less than or equal to 2. Is that clear? I can also ask what is the chance that in a particular over, the number of runs is scored between 1 and 4. I can ask this question also, right? So that would be this value. Would you agree?
Yes, ma'am.
Yeah. Now you can see that the concept of cumulative distribution function is used to ask or answer certain questions, and I need to understand it from the notion of a cumulative distribution function. Okay, so you can see that if I have a discrete random variable, which is again taking the values 1, 2, 3, 4, with this probability mass function, I can set up what is called a probability cumulative distribution function. Whenever a is less than 1, I need to define this a is less than 1, because recall that the cumulative distribution function is defined for all the values on the real line. So for a is less than 1, it will take the value 0. Between 1 is less than or equal to a is less than 2, it will take the value 1 by 4. Between 2 is less than a, 2 up to 3, it will take 1 by 4 plus 1 by 2, which is 3 by 4. Between 3 and 4, it will take 1 by 4 plus 1 by 2 plus 1 by 8, which is 7 by 8. And for values greater or equal to 4, it is going to take the value 1. So you see that this f of a lies between 0 and 1. And a nice graphical way to represent this is through what we call a step graph, because at every point I have discontinuities. So the cumulative distribution function of a discrete random variable is a step graph. Till here, is it clear? Any questions? And you can see that f of a lies between 0 and 1. In fact, I have not included anything here, but this line would be for any value till 1, it is going to be 0. And any value after 4, it is going to be equal to 1. Is this clear?
Yes, ma'am.
yes, ma'am.
Yeah? Okay. So once we introduce what it is, the next important concept is that of an expectation of a random variable. Now, why is the notion of expectation important to us? Okay, the notion of expectation is important to us, and I'll just start with an example. I'll just ask an example. Suppose I'm looking at how many orders. All of us are familiar with these food delivery apps. Suppose my question is, I'm trying to look at number of food delivery orders per hour. So there could be values this X is taking as 0 order, 1 order, 2 orders, 3 orders, or 4 orders. This is food delivery orders I'm getting per hour with probability X equal to X. Here is 0.1, 0.25, 0.35, 0.20 and 0.1. Is this a, so let me write it clearly, 1 second. So X takes the value here, 0, 1, 2, 3, 4, with probability X equal to I, which is 0.1, 0.25, 0.35, 0.2, and 0.1. This is a value. Is it a probability mass function? Is it a probability mass function?
Yes, ma'am.
Yes, no?
Yes.
Yes.
Yes, ma'am.
Right.
Yes, ma'am.
Okay. Now I see if I am basically from a restaurant, this is what I find out. This is the distribution of having no orders or one order or two order or three orders or four orders. Now I as a restaurant, suppose, or as a app, I would want to know how to plan my kitchen capacity, or I want to know how many people should or delivery agents I should have and all of that. So what is the metric I'm interested in knowing? I'm interested in knowing on an average how many orders would I get per hour. Would you agree that that is a metric I would be interested in knowing? Yes or no?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
I know that this is the distribution of orders per hour, but I'm interested in knowing how, on an average, how many orders would I get per hour. So, on an average, this is what I am referring to as a long run average. So, how do I find out this? So, the question I'm asking is, how many orders can I expect in an hour? Okay, and this answer to how many orders can I expect in an hour is what I call the expectation of a random variable. And the way I define this is summation of xi into probability x equal to xi. So for this particular example, what is x into xi for the first one? This is going to be 0. This is 0.25. This is 0.70, this is 0.6, and this is 0.4. And I add this up. If I add it up, I have a 0.95. 0.95 plus it is about 1.95. Is that clear? So what is this 1.95 telling you? What is this 1.95 telling us? On an average, over many observed hours. What am I observing? The restaurant averages about 2 orders per hour. Is this clear?
Yes, ma'am.
Right?
Yeah.
So you can see that this 1.95 is not a value this x actually takes. But what it says is, suppose I observe over a lot of time, over many times, and I get this distribution, I know that on an average, the restaurant is averaging something close to 2 orders per hour. And I can use this information to plan my capacity, or I can use this information to plan my delivery agents. So the notion of expectation is that of a long run average with of a random variable in repeated independent observations. Is this clear, the notion of a expected value? Any questions? Okay. So this I can apply it to the example I just taught, and you can see for the food delivery hour, the practical meaning is once I get this 1.95, this 1.95 doesn't mean that I'm going to have 1.95 orders an hour. I can approximate it to about 2 orders an hour and say that over many observed hours, the restaurant averages, and this is very useful information if I have to plan. Till here, is it clear?
Yes,
Yes,
ma'am.
Yeah. Now, once I introduce the notion of expectation of a random variable, the next important notion that we want to tackle is that of variance. And why is the notion of variance important at all for us? The notion of variance is important because if you look at these three random variables x, y, and z, what is the expectation of x? What is the values x is taking? X takes the value
Ma'am, for which example?
here. Are you able to see the example? I'm on this one. There are three random variables x, y, and z.
Yes.
X takes the value 0. What is the probability x equal to 0?
1.
1,
So what is the expectation of x?
0.
0,
Y takes the value -2 and 2 with probability half and half. What is the expectation of y?
0.
Z takes the value -20 and 20 with again
And
probability
also
half and half. What is the expectation of y? Z?
0.
0.
So I have three random variables x, y, and z, where all the expectations are 0. But what can I talk about the spread? Is x having any spread at all? X is taking one value with complete probability equal to 1, right? Y is taking only -2 and 2 with the same probability, but you see that the spread of z is much larger, -20 and 20. So when I have expectation of three random variables are the same, even though the expectation is the same, I see that it is not telling us anything about the spread. So I need a measure of spread, and this is what I have from the notion of variance. Formally, how is the variance defined? The variance is defined as the expectation of this. If you look at this quantity I'm highlighting, it is nothing but the x minus mu is the deviation of the random variable from its mean. This is the squared mean. So expectation of the square difference from its mean of a random variable from its mean is what is the variance. I repeat, variance measures the square of the difference of the random variable from the mean, and the expectation of that is given to be the variance. A nice computational formula is nothing but this variance of x. If I look at x minus mu whole square, it is x square minus 2x mu plus mu square. Now, when I talk about properties of expectation, the two key properties of expectation is expectation of A into x, where A is a scalar, is A times expectation of x. Expectation of AX plus B is A into expectation of x plus B. These are the two key properties. Okay. Now, if I use the property, expectation of x minus mu square is the same thing as expectation of x square minus mu times 2 mu times expectation of x plus mu square. What is expectation of x? It is again mu square. So I get expectation of x square minus mu square, and this quantity, that is variance of x is expectation of x square minus mu square, is a good computational formula to compute the variance of x. Is this clear? Yeah?
Yes,
Okay. So now, after having introduced what is a probability mass function, the cumulative distribution function, expectation, and variance, let's look at a few discrete random variables. The basic discrete random variable is what we refer to as a Bernoulli random variable. A Bernoulli random variable is a variable that takes the value either 1 or 0. Just simplifying it by expressing it as 1 or 0. But basically, a Bernoulli experiment is an experiment which has two outcomes, and these two outcomes can be failure and success. Now again, I want to be a bit cautious here and say it is not only two outcomes like head or tail. For example, if I am looking at rolling a die and I get 1, 2, 3, 4, 5, 6, and I define the outcome as even outcomes and odd outcomes, that will also be a Bernoulli experiment. Is that clear? I can define it in that way because I can define it as success and failure. So I can allot success to be 1 and failure to be 0. It actually doesn't matter whether what is 0 and 1, but the idea here is a Bernoulli random variable takes two values. So if x is this Bernoulli random variable which is taking the value 0 and 1 with probability of success is p, then the probability of failure is 1 minus p, because I'm just looking at two outcomes. So the expectation of a Bernoulli random variable is, what is the expectation? It would be 0 into 1 minus p plus p, which is p.
P.
Expectation of x square is going to be
P.
So let's look at another example. If x takes the value 0 and 1 with probability 1 minus p and p, what are the values x square will take? If x takes the value 0 and 1,
Ma'am, 0 and 1.
it will also take x. Suppose x takes the value minus 1, 0 and 1. What are the values x square will take?
1, 0, 1.
0 and 1. Suppose x takes the value minus 1, 0, 1 with probability 1 by 3, 1 by 3 and 1 by 3. What is the probability distribution of x square? What are the values x square will take?
Ma'am, 1, 0, 1.
It will be just 0 and 1. What is the probability of x square equal to 0?
Ma'am, why it is only 0 and 1?
If x takes the value minus 1, 0 and 1, what are the values x square will take?
Ma'am, squaring minus 1, it will also give 1.
Yeah. 0,
0 will give 0
1.
and 1 will give
What
1.
are the values x square will take?
0 and 1.
0 and
0
1.
and 1.
Yes.
Right? I'm saying x is taking the value minus 1, 0, 1 with probability 1 by 3, 1 by 3, 1 by 3. What is the probability x square equal to 0? It will be probability x equal to 0 only, right?
Yes, ma'am.
That is 1 by 3. What is the probability x square equal to 1? It will be 1 by 3 plus 1 by 3, which is
1 by 6.
3.
1 by 2.
Is this clear? Yeah? Okay. So now you can see that. And why do I need x square? X square, I need x square because if I want to know what is the variance of x. So you can see that if x takes the value 0 and 1, what are the values x square is going to take? That will also take 0 and 1 with probability 1 minus pp. What is the expectation of x square?
P.
P. What was the expectation of x?
P.
P. So I know that variance of x is expectation of x square minus expectation of x whole square. So which is p minus p square, and I get a p into 1 minus p, and that's why the variance of x is p into 1 minus p. So if I have a Bernoulli random variable, I know that the parameter, so any distribution has what is called a parameter, and this is how I write it. X is this is to tell it is distributed as a Bernoulli random variable with parameter t. Till here is it clear? And what are the important things? The expectation is p, the variance is p into 1 minus p, and this is the distribution. Till here is it clear?
Yes, ma'am.
Right?
Yes, ma'am.
We start with
Yes,
the
ma'am.
Bernoulli random variable. Now the next thing is what is a discrete random variable. Again, a discrete random variable is a uniform random variable is a variable which takes n values with the same probability, uniform probability. Okay, so you can see that, for example, if I'm having x taking the value 1, 2, 3, 4, then the probability is 1 by 4, 1 by 4, 1 by 4, and 1 by 4. The probability mass function would look, it's the same, right? Same height. So this is a discrete uniform distribution. Is this clear? Yeah?
Yes, ma'am.
X takes value 1, 2, 3, 4. This all the length of the bars or the height of the bars are going to be the same. So what would be expectation of this? What is x into 1 probability x? This will be 1 by 4. This will be 2 by 4. This will be 3 by 4. This will be 4 by 4. So you can say it's 1 plus 2 plus the 6, 10 by 4. So in general, it is going to be n plus 1 by 2, and n plus 1 by 2 was 5 by 2, which is my 10 by 4. Till here, is it clear? Yeah? And
Yes,
you can verify that the variance of x and the expectation of x is given by that. The key point is to understand that a discrete random variable, the probability of this discrete random variable, that is x taking each of the values, is going to be the same for all the values. Then a very important discrete distribution is what we refer to as a binomial distribution. Now, even before we go and understand what is the distribution of a binomial random variable, we will introduce the notion of independent and identical Bernoulli trials. Now,
What
a
is the
Bernoulli,
parameter?
yes?
Like, what is the parameter we use to define the uniform distributed discrete distribution?
Here X.
So,
Yeah.
like earlier you told, right?
Yeah.
Bernoulli is defined by the parameter P.
Here
So what
only
is the
n.
parameter?
It depends on
Okay.
what only thing is here, and this is going to be 1 by n. Is that clear?
Okay.
For 4, it was 1 by 4, right? Is that clear?
Yeah, okay. So n is the parameter here.
Yeah. So it depends on n, nothing else.
Oh.
Okay. Like in the Bernoulli, it was P, right? This is the probability of the success. Here I am telling that if I have X taking n values, 1, 2, 3, 4, and it is equally likely to take any one of, so this n defines the discrete random. Is that clear?
Yes, madam. Yeah.
Because
Thank
everything
you.
is dependent on n, right? Okay. So now the next is to introduce you to this concept of independent and identically distributed Bernoulli trials. So let's toss a coin once. Okay. When I toss a coin once, I know that the outcome is a head or a tail. And let me assume it's a fair coin with equal probability. Right? So this is a Bernoulli trial where I can define the head to be a success and tail to be a failure. Now suppose I am tossing the same coin twice. Okay. What is the probability of success in the second toss? Would it be different from 1 by 2 or would it be the same as 1 by 2?
Be the
Same as 1 by 2.
Same as.
Same as 1 by 2. Similarly, the probability of failure is also going to be same. In a sense, the first trial and the second trial are identical. Okay. That is, they have the same probability of head and same probability of tail. Would you all agree?
Yes, ma'am.
And that is what is called identical distribution. And did the probability of getting a head in the second trial depend on whether you had a head or tail in the first trial?
No.
It was independent. So a notion here, instead of rolling a toss, let me give you another example. I have 2 red and 2 blue balls in a bucket or in a bag. I am first picking up a ball and I'm replacing that ball. So in the first trial, what are the possible outcomes?
2 by 4 each.
What
Red,
are the possible outcomes? I could have had a
red and
red ball
Red
or
ball.
a blue ball.
blue.
What is the chance with which I pick up a red ball?
2 by
By
4.
4.
That is 1 by 2 again, right?
Yes.
Blue
Oh,
ball,
Same.
1 by
Same
2.
1 by
Also
2.
1
right? Okay. Now suppose I had a 3 red and 2 blue balls. What is the chance I have picking up the red ball?
3 by 5.
3 by 5.
3 by 5, and this is a 2 by
2 by
5. This is my first trial. Now in the second trial, okay, I'm replacing it. In the second trial, again, how many red balls and blue balls are? Again, what are the outcomes in the second trial?
3 by 5. Same.
Red and blue.
Red and blue. What is the chance with which I pick up a red ball in the second trial?
Ma'am,
3 by 5.
Again, 3 by 5. And blue ball?
2 by 5.
2
2
by
by
5.
5. Here also it's a red or a blue. This is also 3 by 5 and this is 2 by 5. So the chance of you picking up a red ball in the second trial, did it depend on whether it was a red or a blue ball in the first trial?
No.
It was independent. And the distribution of you finding a red ball is the same as what it was. The red or blue in the second trial is the same as what it was in the first trial. So these are what we refer to as independent and identically distributed Bernoulli trials. Is this clear?
Yes, ma'am.
Yes, ma'am.
Yeah, right. So this collection of IID random variables, this is very important. And here comes the notion of a binomial distribution. Who is transcribing this meeting? Swati? If anybody is transcribing this meeting, I'd request them to please stop it. Because we will share the PDF and everything. Okay. I would request whoever is transcribing this to please stop it. Okay. Thank you. So the binomial random variable is, suppose I have n independent. In the earlier case, I talked about, so I'm going to talk about a success and a failure, success and a failure, success and a failure, and I keep continuing here. I have n independents, this one, where the probability of a success is P and the probability of the failure is P. And here I am talking about how many successes I have. Here I have SSS, SFF. Okay, so I can count the number of successes in n independent trials. Then I get what is called a binomial random variable, which is counting the total number of successes that occurs in n trials. I repeat, a random variable, I'm defining x to be a random variable, which is the total number of successes in n independent trials. Then we say that this x is a binomial random variable. What are the parameters? It is n, because I'm looking at how many independent trials, and p, where p is the probability of a success. This is how I'm defining a binomial random variable. Is this clear? Yeah. So if you go back to the success and failure in n things, you can see that if I have all the outcomes, SSSSS, right? How many successes do I have? In n trials, all of them are successes.
Ma'am, and
And
You can see that if I have all the three of successes, what is the probability with which I get a success here? This is P, this is P, this is P. What is the probability of this outcome? Because of independence, I can multiply them. It will be P into P into P. Is this clear? Yeah?
yes, ma'am.
Suppose it is SFF. If it is P is the probability of success, probability of failure is 1 minus P. So SFF is S into P into 1 minus P whole square. Is that clear? So I just list down how many successes I have. If I have SSSF, it is P to the power of n minus 1 into 1 minus P. So this failure can be either at the last failure, or I could have n minus 1 success and 1 failure, and this failure can appear in any one of the n positions. Would you all agree with it?
Yes, ma'am.
Right? So the way I can find out what is the probability that the number of successes is equal to n, it is just this one thing, because all of them are successes. But what is the probability the number of successes is equal to n minus 1? It is this plus this plus this, and this n can happen anywhere. So that would be n. Okay. So the way I can find that out is given by n choose I. P to the power of I into, this is the probability. See, if I split this P to the power of I into 1 minus P to the power of n minus I is I successes and n minus I failures. Still here, is it clear? Suppose I am interested in n equal to 3 and I have, what are the possible thing? I could have all successes. I could have SFS. I could have SSF. I could have FSS. These three will give me what? 2 successes. Is that clear? Yeah?
yes, ma'am.
I could have SFF. I could have FSF. I could have FFS. This will give me how many successes? One
One.
success. And
One.
FFF will give me how many successes?
0.
0.
Right? Now, what is the probability of this? This is going to be P to the power of 3. So, probability x equal to 3 is going to be P to the power of 3. 1 minus P to the power of 3 minus 3, which is 0. So, it will be P to the power of 3. Now, what is the probability x equal to 2? It is going to be p to the power of 2
Yeah.
into 1 minus p, right? But
Yes.
how many times it will happen? It will happen 3 choose 1 because I'm choosing, or 3 choose 2. This S can take any two of these values. So you can see that I use my combinatorial knowledge to see that I'm getting two successes. Out of the three outcomes, these successes can be in any, it can be either first and second, or it could be first and third, or it could be second and third. Is this clear as to how we get the binomial formula?
Yes, ma'am.
Yeah.
Yes.
So this is what is the binomial formula. I say X is a binomial with parameter n and p. What are the values of I? I takes value 0, 1, 2 up to n. This is what I refer to as my binomial distribution. Any questions? So this is the formal distribution, formal definition. I say X is a binomial random variable with parameter n and p that represents the number of successes in n independent and identical Bernoulli trials, okay, where each trial is a success with probability p. X takes the value 0, 1, 2, n with probability x equal to I is n choose I, p to the power of I, 1 minus p to the power of n minus I. Till here, is it clear? This is
Yes.
about a binomial distribution. Now, the shape of the binomial distribution is very interesting. So, if it is symmetric, for example, is this a symmetric distribution? P equal to 0.3 is not symmetric. P equal to 0.5 is symmetric. So, I'm just demonstrating when n equal to 4 and p equal to 0.3, this is skewed to the right. So, n equal to 0.4 and p equal to 0.5, you see I have a symmetric distribution. 0.8, I have a skew to the left distribution. So this, even for the same n, the value of p determines the shape of the distribution as to whether it is left skewed or right skewed or it is symmetric. If p equal to 0.5, it is symmetric. If p is less than 0.5, it is right skewed. P is greater than 0.5, it is left skewed. Now, similarly, for the same p, if I increase the number n, what would happen? So you can see that when n equal to 40 and p equal to 3, you can see that this resembles a sort of a bell shape here, but it is shifted to the left. Now here it is central and here it is shifted to the right. So this is a right skewed, this is a symmetric, and this is a left skewed. Same p but large n, and same n and different p. You have seen that what would happen. Okay. Any questions? Okay. So what is an expectation of a binomial random variable? I know x takes the value 0, 1, 2 up to n with probability x equal to I is n choose I, p to the I, 1 minus p to the n minus I. I already know the expectation of a Bernoulli random variable which takes values 0 and 1. What was an expectation of a Bernoulli random variable? It was p. Agreed?
Yes, ma'am.
Right? So
Yes.
I can represent this x, which is a binomial random variable, as the sum of n independent Bernoulli random variables. Would you all agree with me?
Yes, ma'am.
Yes, ma'am.
Now, what is the expectation of each xi, where each xi is a Bernoulli random variable with parameter p?
P.
Is p, right? So if I have n Bernoulli random variables, what would be the expectation of x? It is going to be p plus p up to n times, which is n into
N.
p. Till here, is it clear?
Yes.
Right? Okay. Now, what would be the variance of x? Again, if I have x and y are independent random variable, variance of x is nothing but variance of x plus variance of y. X and y are independent. So here x1, x2, xn, are they independent?
Yes, ma'am.
Yes. So what would be variance of x1 plus x2? It will be variance of x1 plus variance of x2. So what would be the variance of x here? It would be variance of x1 plus variance of x2 up to variance of xn. What was variance of xi? Bernoulli
P
P into 1 minus P. I add it up. It is NP into 1 minus P. So what would be the expectation of a binomial random variable with parameter N and P? What would be the expectation of a random variable, Bernoulli binomial random variable with parameter N and P?
NP.
NP. What would be the variance?
NP 1 minus P.
1 minus. Till here, is it clear?
Yes.
Yeah, so you can see that the expectation of x is NP, variance of x is NP into 1 minus P. Okay. Now, as we have said that here in a Bernoulli random variable, the two key things were this IID, that is independent and identically distributed. Now, for example, I have something of this kind. Okay, I have a ball with 4 white and 3 black. Okay, I'm picking up a ball. If it is a black ball, then afterwards, how many, and I'm not replacing it. So how many balls are remaining in the box? 4 white,
and 2 black.
2 black. And here, if I pick up a white,
3 white.
3 white
and 3 black. So now you see that the chance of me getting a black ball here was 3/7 in the first trial. Agreed?
Yes, ma'am.
Yes, ma'am.
Now, in the second trial, what is the chance of me getting a black ball?
By 6.
It is 2/6. So this is not identical to this. Would you all agree?
Yes, ma'am.
Now, similarly, what is the chance of me getting a black ball here?
3/6.
So the chance of you getting a black ball in the second trial depends on whether you had a black ball or a white ball in the first trial. So it is that getting a black ball or a white ball in the second trial is not independent of your first trial outcome. Would you all agree with me? Is this clear?
Yes, ma'am.
So here I don't have independent and I don't have an identical trial. So in this case, we go to understand what is a hypergeometric distribution. So what is a hypergeometric distribution? The hypergeometric distribution, there are two things. I need to divide this again into 2 and 2 independent subsets. So let me show that through this particular thing. I have again a population, or I have from a set of capital N items, okay, from a set, it has a fixed number of trials, okay, and from this fixed number of trials, I'm going to choose some items, and the probability of success is not the same from trial to trial. So here, suppose I have a set of capital N items, again black and white balls, okay. I have M black and N minus M white balls. From this capital N, I'm choosing small n items. Is this clear? Yeah? From
Yes.
this is my actual set, capital N. From here, I'm choosing small n items. I know that here I have, for example, I can have 15 here of 8 are of one kind and 7 are black balls. I'm choosing 8 balls. Okay, is it clear? I want to, and I'm telling a random number to be the number of items of type 1. Okay, so number of black balls in this. So what are the chances? How many black balls can I have here? I'm choosing 8 from these 15. What are the values this x can take? X is the number of black balls in the sample. What are the values this x can take?
0 to 8.
It's 0 to 8. Very good. Suppose I'm choosing only 7. Then what are the values this x can take?
0 to 7.
0 to 7.
Suppose I'm choosing 9. What are the values this x can take?
I'm 0 to 8.
Okay, is this clear? Okay,
Yes.
so now I'm assuming here that this is n and capital N, and x is taking value 0 to 1 to n. Then how many ways can I choose n items from capital N? it would be n choose n. Is this clear? Right? Of which, how many ways can I choose x from m? M choose x.
Yes.
And the number of ways I can choose is n minus x from n minus m is n minus m choose n minus x. This is the distribution of what we call a hypergeometric distribution. So let's look at n equal to 7. Okay, easier. This is equal to 2. And here I have 3 black and 4 white balls. What are the values x will take now? Number of black balls.
0 to 3.
Pardon?
0, 1, 2, and 3.
0, 1, 2. Right? What is the probability x equal to I? In the denominator, I'll have 7, choose 2. Okay? And in the numerator, I'm going to have 3, choose I. Okay? And here I'll have 4, choose 2 minus I. Is this clear? Yes?
Yes.
Yes, ma'am.
Okay. So you can see that if I apply the formula, this is how I get the result for the hypergeometric, which says that probability of x equal to I is 12 by 42, 24 by 42, and 6 by 42. Is this a... Now, quickly check and tell whether this is a probability mass function. 24 plus 6, 30, 30 plus 12, 42. If
Yes,
I
ma'am.
add it to 1, it is non-negative. It's a probability
Yes.
mass function. Till here, is it clear?
Yes, ma'am.
Yes.
Right. Now, as always, you can see that what is the expectation and variance. I am not going to prove it here, the expectation. So what are the parameters of a hypergeometric distribution? What all should I know? I need to know what is capital N. Would you all agree?
Yes, small m and n.
I need small n and I also need to know m. These are the parameters. Is that clear?
Yes, ma'am.
Yes.
Right. So the expectation is given by this and the variance is given by this. Now, interestingly, I can write this as n into m by n. Okay. And here also I can write it as m by n. Now, this I can write as n into 1 minus m by n. Okay. This I can write as 1 minus 1 n. This term I can write it as 1 minus m by n. Would you all agree? Yes?
Yes, ma'am.
Yes, ma'am.
And this term, I can write it as 1 minus n by n divided by 1 minus 1 by n. Is that right?
Yes,
Now,
ma'am.
what would happen if n is really large? Here.
Capital N.
If n is really large, what would happen to this quantity?
Almost
0.
0. Then what would happen to this quantity? This will
1.
become 1. Agreed? So what will
Yes.
I have is n is really large. I get n by 1 minus n into 1 minus m by n is the variance, right? Now, does this resemble something that you already know? N into m by n. Suppose m by n, I give it a value, say p prime. Then what is n into m by n? It is n into some p prime. This will be n into p prime into 1 minus p prime. Have you seen some value like this before?
Binomial
Binomial
distribution.
distribution, right? So it might make sense for us to understand what is the relation between the hypergeometric and the binomial distribution, right? So let's look at the graph of the PMF. Now what happens is as this n becomes very large, okay, binomial versus hypergeometric, as n becomes large, just look at it, as n is 500, the blue is the hypergeometric and the red is the red is hypergeometric, blue is binomial. You can see that as n becomes very large, you can see that the probability distribution for both the distributions are the same. Can you see that? Yeah. The blue and the red are almost the same, right? As capital
Yes,
N is large, right? And you see as small n also becomes very large, you can see that the bell shaped is attained. Now, attaining this bell shape is something that drives inferential statistics, and you will know about that in your statistics 2 course. But this is something which I wanted you all to see is, as my capital N becomes large, the hypergeometric distribution and the binomial distribution are almost similar. Is this clear? Right? So the
Yes, ma'am.
last discrete distribution I'm going to discuss today is the Poisson distribution. See, what the binomial distribution said is, okay, I'm tossing a coin, say 10 times. I'm interested in knowing the number of successes in 10 tosses of the coin. But sometimes I might not be interested in I know that I'm tossing the coin 10 times and I'm counting the number of events in this number n equal to 10. But sometimes I might be interested in knowing or counting the number of events, not given that I have 10 tosses, but in an interval of time or interval of space. For example, if there's a traffic intersection, I might be interested in knowing number of vehicles that pass through this intersection in a given period of time. Or I might be interested in knowing that in a given interval of space or in a textbook, how many number of misprints in a page or number of misprints in a textbook. So whenever I'm interested in knowing the probability of the number of events that happen either in a fixed interval of time or space, again it is a count because I'm interested in the number of events. Would you all agree with that? It is a count. So the minute I have a count, I want to model this as a discrete random variable. So this discrete random variable I'm denoting by x, where x is denoting the number of times this count an event occurs in an interval of time or space, and I refer to that as a Poisson random variable with parameter lambda. Let's see what this lambda means to us. Okay, so this lambda is nothing but if I know that these events happen with a known average. For example, I'm telling you that the number of cars that pass through a traffic intersection is, say, on an average 5 in an interval of time, then this lambda is that known average. I can model it as a Poisson distribution. So whenever I'm looking at counting or the number of events in an interval of time or space, I model it as a Poisson distribution. Till here, is it clear? Yes?
Yes.
Any questions here? So as in every case, we are interested in knowing what is the expectation and variance of a Poisson random variable. So when we are interested in knowing the expectation and variance of a Poisson random variable, the expectation, the probability mass function is given by what you see on the screen. So you can see that the probability x equal to the x. So whenever I'm defining or describing a probability mass function, I need to explain what are the values this x can take. So what are the values this x can take? It is taking countably infinite values. You can see x is taking value 0, 1, 2. Is this clear? Yes?
Yes, ma'am.
Right? And the probability x equal to x is e to the power of minus lambda, lambda to the power of x, and x factorial divided by x factorial. Something that we need to understand here is for a Poisson random variable, the expectation and the variance is the same, which is equal to lambda. So this is about the Poisson random variables. Now, where do we model a Poisson random variable? A Poisson random variable, for example, number of vehicles passing through a traffic intersection, number of people withdrawing money from a bank in a fixed interval of time, number of telephone calls that are received per minute in a call center, number of typos in a textbook, number of defects, all these places is where we say that it follows a Poisson distribution. Is this clear? Yeah. And if you go through the notes, we have seen that how we have derived this Poisson distribution. We don't have the time to go through it. But what is important to remember from a Poisson distribution is you're modeling the number of events that happen in a fixed interval of time or space, and the mean or the expected value and variance of a Poisson random variable is equal to the parameter lambda, where lambda is the average of. So if you go back here, you can see that this lambda is the average number of events per interval. Any questions still here?
Madam,
So
one
these
doubt.
Yeah.
Suppose if we say assume that 10 cars are passing through traffic signal in 1 minute, so lambda will be 10 or lambda will be 1 by
1 by
10.
So what is your interval of time? It is 1 minute, right? 10
Hmm.
cars on an average, how many are passing? So if it is 1 minute, it depends on how you're defining the interval, right? So per interval, per minute, 10 cars are passing, then lambda is equal to 10. But suppose I'm having lambda equal in an hour, okay? I'm having 10 cars passing and I'm interested what is the number of cars passing per minute. Then I am going to divide it by 60. Is it clear?
Okay, yes, ma'am.
Yeah. Okay. Now, for example, let's look at a very simple example where we are applying the binomial distribution. Suppose I have a company where 10% of customers return purchases. All of us are in e-commerce and we know that most of us return, right? So on a busy day, 20 customers buy and the number of items, that is the number of returns I see are, so what is on a busy day? So this, I am trying to model the number of returns. On a busy day, 20 customers buy. So what is my N here?
20,
20. And what is the probability of returning?
0.2.
It is 0.1. What I want to understand here is
10%.
so suppose I have two customers. What is the chance with which customer 1 returns?
1 into
50.
0.1. Customer 2 returns?
0.1.
So are they identically distributed?
Yes.
Now, the chance with which customer 1 returns, is it independent of the customer 2 returning?
Yes.
Yes.
If 20 customers buy an item, will this experiment satisfy the requirement of a binomial experiment?
Yes, ma'am.
If I have 20 customers, okay,
Yes,
and I'm
ma'am.
looking at number of returns to be I can define number of returns to be the success of the experiment also. Is it a binomial experiment?
Yes, ma'am.
Then I need to understand what are the parameters of the binomial experiment. So it is 20 and 0.1. Is this clear?
Yes.
Right?
Yes.
Now I know this thing. What is the probability x equal to 5? It is going to be 20 choose 5. Right? X equal to 5 is going to be 20 choose 5 into 0.1 to the power of 5 into 0.9 to the power of 15. Would you all agree?
Yes, ma'am.
Right? This is the probability that, how would I articulate this? This is the probability of 20 customers, 5 customers return. Agreed? Is this clear?
Yes, ma'am. Yes.
Yes.
This is the probability mass function, which is about 3.2% chance, right? But what is the chance that less than or equal to 5 customers return? Is there a difference between these two?
One is
Yes, ma'am.
cumulative
Yes, cumulative and
distributive
Exactly,
function.
5 customers return and less than or equal to 5 customers return. You can see that it is very likely, the difference. This is only a 3.2. This is a very high chance. Is that clear?
yes, ma'am.
What is the
Yes,
chance with
ma'am.
which more than 5 customers return? 1%, which is
1%.
very unlikely. Is that clear? Now, what is
Yes, ma'am.
expression of a binomial random variable? 20 into 0.1, which is 2. How would I this one? So I know that if 20 people buy, what is on an average, how many people can I expect would return?
NP.
2,
20
right?
into 0.1.
2 people, 20 into 0.1, which is 2. So on a typical day, if 20 customers come, I can expect 2 people to return. So I can plan accordingly. Is this clear? From a business perspective, how we can look at expectation and variance. And the standard deviation is about 1.3. So if I have on a particular day about 4 plus returns, okay, then it is more than the standard deviation. 2 plus 1.3 is 3.3. So more than 4 returns on a day is unusual. If it is less than 3, then it is usual. Is this clear? How we can look at how we apply this concept of expectation and standard deviation?
Yes, ma'am.
Yes, ma'am.
Okay, great. So let's move on now to continuous distribution. As I mentioned, when I have a discrete distribution, I am having a random variable which is taking countable number of values. That's what is a discrete distribution. Count. Okay. Whereas when I'm talking about a continuous distribution, I'm measuring. So when I'm measuring, I have infinitely divisible. So I'm not having any more x taking a value x1, x2, x3, so forth. Rather, I'm interested in knowing x belonging to a particular interval. This is discrete. This is continuous. Is this clear? Yeah.
Yes, ma'am.
Yes, ma'am.
In probability mass function, I define probability x equal to xi. Whereas here, I'm not talking about probability x taking a particular value. Rather, I'm interested in probability x belonging to a particular interval. Is this clear again? Now that is given by a probability density function, and this density function is nothing but what is the chance. So now suppose I have a density function. A density function is equivalent to that of a probability, whatever the probability distribution function said in the discrete case. I am having a density function here. And what is the property? Just as I had p of x equal to xi should be greater than 0, I have f of x is greater or equal to 0. I had summation probability x equal to xi should be equal to 1. Here integral over the set I'm defining f of x should be equal to 1. This is how I define a probability density function. Is it clear till here? Right? So what are the common continuous distributions? One of it is the uniform distribution. What do I mean by a uniform distribution? Suppose I have A and B here, and this is the density function. The probability that I find this random variable between A and B is the same. In other words, it is a constant. So f of x is k for x between A and B. Till here, is it clear? Now, I know that the area of the curve under this. So, this is a rectangle. What is the area of this rectangle? This is K, this is A, and this is B. So, what is this? This is B minus A, right? Would you all agree?
Yes.
Right? So, what is the area of the rectangle? It is K into B minus A. Now, what is the property of this area? What should this area be? It should be equal to 1. Agreed? Because that is the density. A
Yes,
to
ma'am.
B, f of x dx should be equal to 1, right? So, this is 1. So, what is the value of this K? It is 1 by B minus A. Is this clear? So, the probability density function is 1 by B minus A for A less than x is less than B. Now, is there a difference between A less than or equal to x is less than or equal to B? A very important thing that we need to know is if I have a continuous random variable, probability x equal to xi is equal to 0. Why is it equal to 0? Because I know that x does not take a particular value. I know that x belongs to a interval. Is this clear? Yeah. So I need to be very careful and understand that x equal to xi, that if a continuous random variable is going to take the value 0. So if I have a uniform distribution, f of x is 1 by b minus a, for a is, I can write it as less than or equal to x to less than or equal to b. One of the most important distribution is a distribution where a equal to 0 and b equal to 1. And I refer to that as x is uniform 0, 1. This uniform 0, 1 is a very important building block when you're generating what is called as random numbers. But what is this uniform 0, 1? So my f of x was 1 by b minus a. If b is 1 and a is 0, it is just equal to 1. So as 0 is less than x is less than 1, f of x is equal to 1 and 0 otherwise. I can verify that it is a PDF with f of x greater or equal to 0 and 0 to 1, f of x dx equal to 1. This is called a standard uniform distribution. Now, the cumulative distribution function for a discrete random variable was a step function. What is it for a uniform distribution? I know that f of x is equal to 1 by b minus a, for a is less than x is less than b. So I have a here, I have b here. Okay, so what is f of a? F of a is probability x is less than or equal to a. What is probability x is less than or equal to a? I know
0.
x is 1 by b minus a, for a less than x is less than b, 0 otherwise. So f of a, for all these values of x which is less than or equal to a, what would be f of x? F of a? F of x, it is going to be equal to 0. Is that clear? Right. At a, what it is? It is actually, it is 1 by b minus a. So what is happening at this point? It is, suppose I'm looking, so f of x is minus infinity to x, f of x dx, or f of a is minus infinity to a, f of x dx, okay, which is same as a, let me not write it as a again. So let me tell as f of x is a to x, f of x dx. Okay, for x less than a, I know it is 0. For what would happen at, what is f of x? It is 1 by b minus a to x dx. Okay, so what would this be? This would be just x minus a by b minus a for any x between a and b. Would you all agree? Yes or no? Yes? Is this clear how I got this f of x for any x between a and b?
Yes, ma'am.
Right? Okay. Now I want you to look at this carefully. This I can write as x into 1 minus b by a minus a by b minus a. Right? So I have f of x, which is of the form m into x plus c. What is this? Does this, what is this? This is the equation.
Straight line.
Equation line.
Straight
A
line.
line, right? So you can see that the cumulative distribution function here is going to be, for x less than 2, it was 0, greater than 4, it is 1, but between here, it is a straight line. And if x is a uniform between 2 and 4, the slope of that line is 1 by b minus a, which is 2. So you can see that here, this distribution function, the cumulative distribution function, is no longer discontinuous. You have it as a continuous function. Is this clear? Cumulative function of a uniform distribution.
Yes.
Right. Now, just as we defined what was a expectation in the discrete random variable case as summation x probability x equal to x, and variance is also, we defined it as expectation of x square minus mu square, or expectation of x square. In the continuous case, expectation of x is x into fx dx, okay, over the range of distribution. So if I have x is equal to a uniform a to b, my expectation of x is going to be a to b. What was f of x? 1 by b minus a into x dx. Is this clear? Yes? Expectation of x. Now what would this be? 1 by b minus a. What is integral x? a to b dx. What is this?
X square.
X square by
X square by 2, right? A to b. Is this clear? So what would I have? I'll have a b square minus a square by 2. Would you all agree? Again, I can write this as b minus a into b plus a, b minus a by 2, which I'll get b plus a by 2. So the expectation of a continuous random uniform random variable is a plus b by 2. Is this clear? What would the expectation of x square be? Quickly. What would expectation of x square be? This would be x square. So this would be x cubed by
cube by 3.
3.
b cube minus a cube by 3. Right? So I'll get what is expectation of x square and leave it as an exercise for you all to verify that the variance of x is going to be b minus a whole square by 12. So now I have got what is the density of a uniform distribution. So when I looked at a discrete random variable, I talked about a probability mass function, the distribution function, the expectation, and the variance. Same for continuous random variable, I'm talking about a probability density function. I obtain the cumulative distribution function. I obtain the expectation and the variance. Now, what are the parameters here? The parameters are A and B. Till here, is it clear? Any questions? Is it clear, please?
Yes, ma'am.
Yeah.
So now, once we have this, what kind of problems can you expect? For example, the straightforward problems are given x is a uniform random variable. What is the probability x is greater than 1 by 3? What is the probability it lies between some value? And what? So see here, now what I want you all to see are these two. What is the probability x is greater than 1 by 3? Is 1 by 3 to 1. F of x is 1 dx, which is 2 by 3. Is that clear?
Yes, ma'am.
Yes.
Probability x is less than or equal to 0.7 is 0.7. Now here between 0.3 and 0.9, okay, it's just 0.6, which is the same as 0.2 and 0.8 also, okay, which is also 0.6, where I'm just looking at 0.2 minus 0.8 minus 0.2 and 0.9 minus 0.3. Whether it is less than or equal to, again in a uniform case, I think this has to be taken care of because I'm looking at it as a limit of the integral. Okay. Now this example, I'm just going to skip it over here. This is the same example that we discussed in the lecture notes. So I'll just ask you to go through it. The next thing is a triangular distribution. Now what I have displayed here is what we refer to as a symmetric triangular distribution. Now this symmetric triangular distribution, again you can see that this is the triangular distribution. So what is the density of this triangular distribution? Okay. Now let's look at what is the area under this curve. What is the area under this curve? Can you quickly tell me what is the height of the triangle and what is the area of this curve? What would be the area under this curve?
4 units.
Half into base into height.
What is the base?
Base is 4.
4. What is the height?
2.
2. Okay.
Yes,
So
ma'am.
what is the area?
Half into
4
1.
units.
into height. So half into. So
4
4.
into- Pardon?
Should be 1,
4
madam,
units.
area under the triangle.
4.
So what is the problem? So what is the density? So what would be the density?
Ma'am, 4.
How would I give this f of x? How would I define this f of x now? It's a triangular thing. This is a line here. So just look at this now. Forget about the other part. What would be this f of x here? This is a line, right?
X
So
equals
how
to
would I define f of x? That's what I'm asking. If x is 0 is less than x is less than 2, what would f of x be? 2 is less than x is less than 4, what would be the f of x?
0 to 2 it is x and 2 to 4 it's minus x.
Minus x? Will it be minus
Then,
6?
0 to 2, it will
And
be
f of x, so if
1
x is
minus
equal to 2,
x.
is it minus 2? F of x has to be greater or equal to 0, right?
Yeah, yeah.
It should be x
So
minus
what
2.
will it be? Is it minus x?
X minus 2. X minus
X
X
2.
minus
minus
2
2.
or what is it? Think about it.
Ma'am,
It should be
2 to 4, it will be minus x.
Minus x. That's what I'm saying. If it is minus x, if x equal
it should
to
be 2 minus x.
2 minus x or 4 minus x?
4 minus x.
Think about it. Okay, this is again something we have done, but I want you to see how the density function is defined. Is that clear? Remember density f of x, if it is minus x, will it be a density function?
Yeah, ma'am.
What is that thing I need from a density function? I need f of x to be non-negative, right?
Yes.
Yeah.
4 minus
Yes, ma'am.
x.
Right?
So we are tried 4 minus x.
4 minus x.
Minus
Is that
x.
clear? So you can see
Yeah.
that using that you can find out what is the height of the curve and everything. You can just define it and you can find out what is the probability density function. Now a very important density function that is typically used especially in queuing theory and in reliability is what we refer to as an exponential distribution. The density is actually here given by f of x is lambda e to the power of minus lambda x. Lambda is a parameter. Okay, it is said to be an exponential with parameter lambda. This is especially in queuing system and Markovian systems, this exponential distribution is extremely important. Now, the shape of this curve for different values of lambda, you can see it is, this follows the distribution for different values of lambda, lambda equal to 0.5, 0.1 and 2. And you can see that the cumulative distribution function is probability x equal to a, 0 to a. Why is it 0 to a? Because I have x is greater or equal to 0. I have defined the density for x is greater or equal to 0. So you can see that this is 0 to a, lambda e to the power of minus lambda x. Now what is this? This is nothing but lambda minus e to the power of minus lambda x, because lambda and lambda would cancel. And this f of a is 1 minus e to the power of minus lambda a. So when I'm talking about an exponential distribution, this becomes extremely important. What is the two things I need to know about a distribution? I need to know the density of the distribution. I need to know what is the cumulative distribution of the this one. And what is the parameter? Parameter is lambda. What do I know about this lambda? This lambda is expectation. If I know x is an exponentially distributed random variable with parameter lambda, then what would be the expectation of x? It is going to be, I know again the expectation of x is going to be what? It is again, I know this f of x is given to me. So expectation of x is going to be 0 to infinity x lambda e to the power of minus lambda x dx. I can show that this expectation of x is nothing but 1 by lambda. Okay, and I can show that the variance of x is 1 by lambda square. This we can show through what you already have learned in math, which is called as integration by parts. I can show expectation of x is 1 by lambda and variance of x is 1 by lambda square. So the key things that you need to understand from an exponential distribution is what is the density function, what is the cumulative distribution function, what is the expectation, what is the variance, and what is the shape of the distribution function. A quick application is, suppose the length of a phone call in minutes is an exponential random variable with parameter lambda equal to 0.1. Somebody arrives immediately ahead of you at a public phone booth. Find the probability that you'll have to wait for more than 10 minutes. So what is it I'm asking? I'm asking probability x is greater than 10. I know probability x is less than 10 is f of 10. I know what is f of 10 is 1 minus e to the power of, that is something which I already know, right? I know f of x is 1 minus e to the power of minus lambda a. I'm asking probability x is greater than 10. So probability x is greater than 10 is 1 minus probability x is less than 10. Is this clear? Yeah. Now, I know this probability x is less than 10 is 1 minus e to the power of minus lambda into 10, which is e to the power of minus lambda into 10. Do I know what is lambda? Is lambda
0.1.
given to me? I already know lambda is 0.1. Is it clear? So 0.1
Yes,
into
ma'am.
10 is 0.1. So it is e to the power of minus 0.1, which is 0.368. So there's a 0.36 probability that I'll have to wait for more than 10 minutes. Is it clear?
Yes, ma'am.
Right? So you
Yes,
can see that I can answer whatever this, based on what I have, this should be 0.1, sorry. I know this x, and similarly, between 10 and 20 minutes also, I can compute these probabilities. So where is exponential distribution used? Exponential distribution is a distribution that commonly arises when you want to model what is called inter-arrival time or service time. You model it as a exponential distribution. It's a very, very useful distribution to model inter-arrival times and service times. The last distribution I was asked to talk about is the normal distribution. So Swati, I'm just going to briefly tell about what is normal distribution. Can you tell me till where it is expected that we should talk about normal?
yes, ma'am. We just have to introduce the normal distribution, like they can solve the FZ.
That's it, right? Nothing more.
Yeah.
Okay, right. Thank you. So why is the normal distribution so important to us? See, the normal distribution is something that arises in a lot of applications. We keep listening, as I showed even in the binomial, you saw that at some point everything reached what is called a bell-shaped curve, right? All of us saw that. Okay, we saw that everything reached what was called a bell-shaped curve. So the normal distribution now is defined by two parameters. One is what is called the centrality or the mean of the distribution, and the other is what is called the spread or the variance of the distribution. So the two parameters of the normal distribution, and I write x is a normal with mean mu and variance sigma square with this particular density. Now let's look at the density function clearly. At x equal to mu, what happens to this density function?
One by root 2 pi into
Ma'am,
sigma.
symmetrical.
What at x equal to mu, what would happen here?
The curve is symmetrical about.
So that is what we refer to as the height of the curve. Is that clear?
Okay.
Right? At x equal to mu, okay, this is if I'm plotting x and f of x, at x equal to mu, I have the largest height. Is that clear? Now, as x moves away from mu, I'm going to have, so this is what I refer to as the height of the curve. And what is the height of the curve? It is nothing but 1 by root 2 pi sigma. At x equal to 2, you see that the height is just 1 by, because at x equal to mu, I'm going to have this quantity not going to contribute anything as the significant. So it will be just, this is the height of the curve at x equal to mu. And you see that the curve is symmetric along. And why is the symmetricity coming? You can see that the symmetricity is because of this x minus mu whole square. So it is symmetric about the mean. Is this clear?
Yes, ma'am.
Yeah, right. So the normal distribution is a distribution which is giving us, so you can see here for this x, for the same mu, but different sigma, you can see that the height is 0.798, whereas the height here was 0.399 for mu equal to 2 and sigma equal to 1. And here it is mu equal to 2 and sigma equal to 0.5. And that is what is defining the height of the curve. And it is symmetric about sigma. And since it is a normal distribution along the mean, this is how the curve usually looks. Okay. It actually does not meet the x-axis, but it is more asymptotic to the x-axis. The area under the curve has to be equal to 1 because it is a density function. And it can take values between minus infinity and plus infinity. So if I have, suppose an x which is having a mu of this and variance of this, you can see that and I have another mu, this one with the same mean but a lesser variability, you see that this curve should be this way because the area under both the curve should be equal to 1. Sometimes if you plot this is incorrect. Why is this incorrect? Why is this incorrect?
Area is
Here the area, so the area, so this is incorrect. So you can see that this has the largest deviation, this has the least deviation. So the height of the curve is different. Is this clear? This is the first understanding that we need to know, is when I'm plotting the density of same mean and different sigma, the larger the sigma, the flatter and more spread, and the lesser the sigma, the more peak. Is this clear? Similarly, if I have same sigma and different mu, how will it look? Same sigma and different mu, it's going to be this way. Is that clear? Right? Different mu's, but same, the deviation, this variation is the same. So same sigma and different mu's will look something like this. Is this clear?
yes, ma'am.
Yes, ma'am.
Okay. Now, one key property about the normal distribution is it is a distribution which is symmetric about the mean. What does this mean? It means that the purple shaded region and the green shaded region are the same. It tells that X is equally likely to be on either side of this mean. That is what it means. So, how do I express it mathematically? The probability X, what is the total area under the curve? If it is a normal distribution and density distribution, what would be the total
One.
area under the curve?
1.
It is 1. Okay. And I'm saying that this purple area and the green area are having the same area, right? The purple plus green is equal to 1 and purple is equal to green. So what would be purple and what would be green?
0.5.
It would be half.
1.5.
Right, and that is what I'm writing as the mathematical expression, which is saying that the probability X is less than or equal to mu is same as probability X is greater or equal to mu, which is equal to half. Because purple plus green is equal to 1. Purple and green is equal. So probability of purple is equal to the green, which is equal to half. Is this clear?
Yes, ma'am.
This is the
Yes.
property which is the symmetricity property of the normal distribution about the mean. For general mu, so and general sigma, this is a bell-shaped curve which is symmetric around the mean and it is also centered around the mean mu. And this is very important is what is called the approximation rule of a normal distribution. What is the approximation rule says? If I have a random variable that is following a normal distribution with the mean mu and sigma, I know that it is symmetric around the mean. All of us agree to that? Yes?
Yes, ma'am.
68% of the observations will lie within 1 sigma of the mean. So what is within 1 sigma? Within 1 sigma is mu minus sigma to mu plus sigma. So the blue shaded region is giving us the percentage of observation or a normal random variable with a mean and standard deviation will be between mu minus sigma and mu plus sigma with probability 0.68. Between mu minus 2 sigma and mu plus 2 sigma with probability 0.95. With between mu minus 3 sigma and mu plus 3 sigma with probability 0.997. This is what we refer to as an approximation rule. Now, why do we care about this approximation rule? So now let's imagine that I have 100 students in a class and I am telling that the marks obtained by the 100 students in say statistics 1 is following a normal distribution with mean 75 and standard deviation 5. I repeat, what is the mean?
75.
75. And what is the standard deviation?
5.
Okay, right. So how many students can I expect to be within 60? What is mu minus sigma?
70.
Mu plus sigma?
80.
80. So what is the percent or what is the probability of students getting, or what is the probability that this mark will lie between 70 and 80?
0.68.
0.68.
0.68.
Right? Between 75 and 80?
0.34.
And why is that? Because of symmetricity. Is that clear?
Yes, ma'am.
Yes, ma'am.
Right. Between 80 and 85? Okay. Let me ask you this. Between 70, what is mu minus 2 sigma? 65 and 85. How many people would have got? What is the probability of finding marks between 65 and 85?
0.997.
0.95. Between, what would it be between, what is this area? What is the probability of this area now?
That is
This entire is 0.95. So what is only this area?
0.13. 0.13.
Okay, so now is this clear how you can work it out?
Yeah.
So what would this area be? This would be 0.95 by 2. I already know what would this be. This is 0.34, right? So this would be 0.95 by 2 minus 0.34. Is that clear?
Yeah, ma'am.
And what is this entire area? It is 0.997. So this would be 0.997 by 2. Again, I can find what would be the percentage of people in this narrow brown, right? So what do you think would be the number of people who would have, what is the probability of finding what is mu plus 3 sigma in this case?
90.
90.
So what is the chance of finding a score which is greater than 90? Do you think it is very high or very low?
Low.
Very low.
Very low. Similarly, what is the chance of a score which is less? What is mu minus 3 sigma?
60.
It's 60.
60 mu minus 3 sigma.
Yeah, 60.
60, right? Okay. So you can see that the chance of finding a score which is greater than 3 sigma and less than 3 sigma is very less. Is this clear?
Yeah.
Okay. And this is what we say is grading on the bell or grading on the normal curve. Most of the places we, if you have large classes or something, this is somewhere where we like to, where people might, many places, this could be an S grade, this could be an A grade. Now this could be again a B, this could be C, this could be D, and we know that the number of percentage of people who would lie in each category can be easily determined. Is this clear? This is if something follows a normal distribution. Is this clear?
Yes, ma'am.
Right. Now, this is for a normal distribution. One of the key things in a normal distribution is what we refer to as a standard normal distribution. A standard normal distribution has a mean of 0 and variance of 1. So, all the things that apply to an actual normal applies to a standard normal, except that between minus 1 and 1, minus 2 and 2, and 3 and 3, the distribution is 0.68, 0.95 and 0.997. Why is the standard normal important? Because whenever we talk about a normal distribution, we represent a standard normal distribution with a z. And I can find out easily z is a standard normal distribution with mean 0 and variance 1. And I can just apply the approximation rule to find out these various quantities. So the application of approximation rule becomes very simple. For example, what is the probability of z greater than 3? Just tell me, what would be the probability of this? It is almost 0. Less than 3?
0.
Minus 3?
Minus 3.
Yeah,
Okay.
almost
Now
zero.
greater than 1?
1 3.
Less than 1. Let's do less than 1. What is less than 0?
0.34.
Less than 0.
0.5.
0.5. 0 to 1?
0.34.
0.34.
Less than 1?
0.84.
Very good. So greater than 1?
1 minus 0.84.
0.16.
It must
Very
be
good.
1
Okay, less than minus 1?
0.16.
Less than minus 1?
Again 0.16.
Right, is that clear? So now you get, so it is very easy for us to, once we know the standard normal, and this standardization is what we call that if x is a random variable, x minus mu by sigma is what we call is a z-score. So if I want probability x is less than a, I just standardize it and it equivalent is probability z is less than a minus mu by sigma. So the standard normal variable is useful for us to achieve what we refer to as standardization of a normal variable. Okay. So with this, I think we completed what we started out with. So what was the agenda of today? The agenda was today was to revisit the concept of what is a random variable. We introduced the concept of a probability mass function, cumulative distribution function, expectation, and variance. In particular, we looked at particular discrete variables. We started with the Bernoulli, went on to the binomial. In the binomial, it is very important that we look at IID, it is independent and identically distributed. When this fails, we saw what is a hypergeometric distribution. And then we saw that as n, capital N increases, the hypergeometric and the binomial almost are the same. Then we also introduced what was a Poisson distribution. We went on to establish the equivalence of a probability mass function with what is called a probability density function. We also looked at the cumulative distribution function for a continuous random variable. We started with the uniform distribution. Then we looked at the exponential distribution. And finally, we looked at normal distribution. In the normal distribution, we spent some time to understand what was the approximation rule or the empirical rule in the distribution of the normal variable. Okay. Any questions? I'll be happy to take them. Clarifications?
No, ma'am.
Okay. Okay. In that case, thank you all. Wish you
Ma'am,
all the best for your exams.
Yeah,
Thank
ma'am.
you, ma'am.
As we are coming into this course, can I ask you one question?
Sure.
So next course which we are going to opt is statistics 2, right? So according to you, what are the very important concepts which we need to clear before taking statistics 2 as well as math 2 from this course?
I think every concept is important.
Okay. Like the major concept which
Major
the deep
under-
understanding, like deeper understanding which concept we need. That's what I wanted to ask.
See, if you look at it, when you look at the first module, it was only, we did not introduce any randomization there. It was just descriptive statistics, right? Completely
Yes.
descriptive. But we, nevertheless, we introduced the notion of measures of central tendency and measures of variation there. Right?
Yes,
And when we had more than two variables, we introduced the concept of association. That was in a descriptive space. Right? But the minute you come to random variables, you are introducing the same concept but under uncertainty. That's what randomness is under uncertainty. Would you all agree?
Yes, ma'am.
But whether it is a variable or a random variable, finally statistics is about extracting information.
Yes, ma'am.
And what do I mean by information? I need the measures of central tendency. How do I summarize my data? Right? So all the questions that I asked in the descriptive space is going to be the same questions I'm going to ask in the uncertain space also. Agreed?
Yes, ma'am.
Right? But to understand uncertainty, I need to understand probability. So you see that without the notion of probability, I could not have defined what was a probability mass function or an expectation or a variance of a random variable.
Yeah, ma'am.
Okay, so that's why we introduce the notion. So as you go to statistics 2, you will have the notions. Here we start with the probability mass function of a single variable. There you'll start learning about joint distribution. Just as in descriptive statistics, I learned about association between two variables. You're going to look at joint distribution between two variables, right?
Yeah, ma'am.
And you'll be looking at conditional distributions also there. For that, I need to understand my probability. So that's why we call this the foundation course. This course is giving you all the foundation that you need to go for the higher level course. Okay. So in my opinion, a conceptual understanding of everything is very, very important.
Yeah, okay. Thank you.
Okay. Right. Any more questions?
No more from my side, ma'am. Nice
Okay.
meeting.
Thank you. Thank you all. No more questions. Wish you all the best. Thank you all. Good night.
Thank you, ma'am.
Thank you.
Thank you, ma'am.
Thank you. Yeah. Thank
Thank
you.
you, ma'am.
Thank you, ma'am.
Thank you. Thank
Thank
you.
you.
Thank you all. Thank you.
Thank you, ma'am, for the today's session.
Thank you.
Yeah.
Thank you.
Good night, ma'am.
Good night. Good night. Thank you.